Okay, so we want to test, or we want to do the problem. The curve formed by y equals square root of x and y equals x rotated with those two curves that look like and the line x equals 1 and the y-axis. So the curve formed by rotating this around the x-axis. Really, we're just trying to demonstrate the use of the shell method here. This is going to be we're going to use the shell method, which may not be the easiest. It may be easier to do the disk method for this solid that's formed, but we're just really going through the motions of using the shell method and derivation of the formula for the shell method. Alright, so this is y equals the square root of x. This is y equals x. Here's 1. This is where they meet. We know this is where they meet because we set them equal to each other. You know, square root of x equals x where. So we know this is the same as x to the 1/2. So we divide both sides by x to the 1/2. So we have 1 equals x over x to the 1/2 is equal to x times x to the negative 1/2 is equal to x to the 1/2. So 1 is equal to square root of x is plus or minus. So x equals plus or minus 1. But since we're limited to the y-axis, we're not gonna worry about this part over here. So our solid is right here, and we're gonna rotate it around the y-axis. All right, now here's where it gets to be a little bit tricky. The visualization of the solid that's formed after you rotate it. Okay, I think one good way to do that is to picture a few points on here. As a matter of fact, I think I've seen it explained where you take one shell in this area. So say the shell is right here. Let's shade it in. Okay. This shell is formed, or this piece of the two-dimensional area, when you rotate this around the x-axis, the y-axis. Sorry about that. When you rotate this, we're calling a shell here. The rectangle. When you rotate this, it's a little bit easier to picture. You rotate this thing around. What you'll have is a cylinder to look like this. Okay, and so as you have a bunch of cylinders like this, you have one right here, one right here. You have a bunch of cylinders. Those cylinders will make up this shape rotated. I'm going to insert some links here to show kind of visually through graphics and through the program what it looked like. Okay, so how do we derive the area or the volume formed by this shape that results from rotating this thing around the x-axis? Okay, what we want to do is we want to take this cylinder and use integration to arrive at the areas of these cylinders. We're going to take we're going to look at the area of one cylinder, and then we're going to use it. We're going to integrate it all across this region from 0 to 1, so that we'll have the entire volume encompassed. Alright, so the way that they explain it, this is one sample shell. Alright, this is this shell. The way we're going to do it is we're going to take this shell and split it right here down the middle, or think about it like that. We'll have and roll it out. This piece right here at the top is the circumference. Imagine splitting it right here, and you open it up. So this piece here is the circumference. Alright, now what's the circumference of a circle? Two pi r. Alright, the radius is here. Okay, so what's the radius? The radius is right here. Okay, so the radius, this translates to this. The radius is right here. Okay, it's hard to see. I'll probably have to draw it over. What this radius represents is x, or this radius can be represented by x. So we know this is equal to 2 pi x. Of course, I'm going to have to probably do this whole thing over, because I know it's sloppy. But it's just 2 pi x, alright? So that's the circumference. Now, the area, we're trying to find the area of this thing, and it's hollow. Alright, you understand that it's not completely filled in. Alright, so what is this distance here? The distance right in here, in this wall. Imagine a can of soup. Okay, and we're trying to find the volume of the can itself, and it's hollow, so not the soup itself, but just the can. So we have the top. We found that circumference. We know that. Now we're trying to find the wall. The can, it has something. It's very thin, but it has some thickness. All right, that thickness is going to be represented by dx in this instance, because that's this thickness. All right, it's infinitesimally small, but we're going to use integration to let it cover the entire surface. So this is really dx. The confusing thing that I found on this is that we're looking at dx and x. See, x is in the same exact direction as dx. So it's like, how can we say x and dx? The thing about it is x is represented by the radius, or the radius is represented by x right here, and that's just this distance from 0 to wherever. That shows where the radius is, the different average points here. So we have one right here. We rotate this one. The radius is going to be from here to here, represented by x. Okay, so that's how you have dx in one hand and x in the other hand. It's x, x, x. It's always x. Even when it's here, it's 0. Alright, but then if you move out a little bit, it's going to be x. So then you have dx is the thickness of the wall here. And what else is left? The height. Okay, so the height is represented by this function, or this dimension, this side. You know, the thickness of it is dx, but then the height, then I'm representing the thickness by like this shadow. Okay, it has some thickness. This wall, this piece of metal. When we took this can of soup and we cut it right down here and we opened it up, it's thick. All right, the soup is like this now. It's thick though. It's dx thick. And how high is it? We know this is the circumference, but how high is it? It's determined by this distance from here to here. Okay, this is the height. All right, this is the height. Okay, so 9 minutes already. Good night. All right. This is the height. Let me stop it here because I know we got a limit of 10 minutes. So I'm going to stop it here.